All right, good evening and happy Sunday to everyone. I hope you enjoyed your day. So, we have a couple of things to cover in tonight's class. Hopefully, we can exhaust more questions on limits, and that's using the L'Hopital rule and the simplification rule. And also, if we should be able to touch the theory around continuity and discontinuity. And also, it would be great if we can get into the first principle of differentiation tonight. So, I welcome you guys once again. Welcome to tonight's class. It's going to be great. And I really hope you can pay real attention, get your jotters and your writing materials, and ensure that you get the best from tonight's class. All right. All right. First of all, I want to be sure that everyone can hear me. Yesterday we had some things around limits, and I should be pretty sure now that you have a better understanding of the theory around limits. And I want us to get into some more questions today, majorly because what we're doing is not just focusing alone on limits, but it also builds up your ability to solve questions, especially circular functions, which is one of the most misunderstood aspects of calculus. The general algebraic aspect of calculus, when you have, for instance, 5x squared minus 2x, if you're asked to differentiate this, many people don't have issues with this. It's quite simple for many students. But you see, when you start having sec x plus x cos x, things like this is where people have issues. And that's why the questions we are solving, as much as they are focusing on the theory around L'Hopital and all the other things we talk about, but I also see it as an opportunity to build up your ability to answer questions around circular functions. So I told you guys already yesterday, the key to solving circular functions, number one, is for you to know the identities. So if you really want to enjoy tonight's class, make sure you have those identities close by. And when I talk about identity, I'm referring to the table that tells you that when you differentiate sine x, you get cos x. When you differentiate cos x, you get minus sine x. When you differentiate tan x, you get sec square x. When you differentiate cosec x, and so on and so forth. The table that shows you all those things, I really love if you have all these things somewhere around you, because you would not be second guessing what we are doing. So because we'll be using that a lot. So if you have that, please make sure it's close by. Now let's I gave you a question yesterday. Let me solve it. And for those of you that you probably had some issues yesterday, this is yet another opportunity for you to understand this much properly. So look at this question. You are told to find the limit as x was tending to 0 of this function. What was the function? It was a fractional function that had 1 minus cos x over x squared. All right. Now you want to find the limit of this. Now, I told you guys already yesterday that the very first thing you want to do, the first and foremost thing is for you to directly substitute your x, whatever your x was tending to, you directly substitute it into the function. So let's try and do that here. X was tending to 0. So obviously, we're going to be putting x as 0. So we have, instead of cos x, now we're having cos 0. and we have 0 squared. This will be, cos 0 is 1. This will be 1 minus 1 over 0. 0 squared is 0. And this will obviously end at 0 over 0. Now, it is when you arrive at this point, that is when you start to decide to use either simplification or L'Hopital rule. So you don't just go straight to using L'Hopital rule. This is what we call an indeterminate form, when you have infinity over infinity or 0 over 0. Now that we have arrived here, we know already that we have to use one of the two. So one of the things I did yesterday was I decided to use both methods. And the reason why I'm doing that is so that you have flexibility. So we're going to initially use L'Hopital rule. And if you remember yesterday, I explained to you that L'Hopital rule is quite simple for every student to understand. What do you have to do? Differentiate, find the derivative of the numerator and find the derivative of the denominator separately. And then you will now make that as a new function. So this is what this means. So I'm going to call the numerator fx. I'm going to call the denominator gx. So fx was 1 minus cos x, all right? And gx was x squared. So what I want to do now is to go on and find the derivative of the numerator. If I want to differentiate this, of course, differentiating a constant value gives you 0. Now, differentiating cos x, that's why I said you have to have this table close to you. When you differentiate cos x, this is a circular function. What do you get? When you differentiate cos x, you get minus sine x. Now, look at this. Differentiating 1 gives you 0. Differentiating, we have a minus here. Then when you differentiate cos x now, you get minus sine x. Now, what I wrote here now, minus sine x, is not something you have to ask me, how did I do that? There's a table for this. Go and get that table and get all these things close to you. Now, that means our final answer now will be 0 plus sine x, which will be sine x. All right, that's that about that. Now, for the denominator, we have to go on to find the derivative of the denominator, which was x squared. If you differentiate this, this will be 2x. All right, so now we're going to have a new function using this derivative. So now let's go on to have our new function. X tending to 0, now we are having sine x over 2x. All right, now the next thing you have to do is to fill in the value for 0 back into this again and try and see if you're going to get an answer different from an indeterminate form. So let's fill this in. Putting x here, we have sine 0 over 2 times 0. Sine 0 is 0, 2 times 0 is 0. Could you see what's going on here? Once again, we are arriving at an indeterminate form. What do you do again? You don't have to get confused. L'Hopital rule accepts you to keep on finding the derivative until you get the right answer. So at this point, when the first derivative did not achieve what you wanted, you are still getting an indeterminate form. You have to go on to find another derivative, of course, now of this one. So let's see this way now. We have f of x was sine x. This was what the numerator here, and the g of x was 2x. So we want to go on now to find another derivative. In this case now, we represent this as f prime prime of x, and this one will be g prime prime of x. All right, now what do we want to do now? How do we differentiate sine x? What do we get? When we differentiate sine x, it's something you need to know. This is a table. It's not something we have to say so much about. The table says when you differentiate sine x, you get cos x. And when you differentiate 2x, you know that will give you 2. All right, let's use this spot right here. So we have a new function now. What's our new function now? We are having limit as x tending to 0. This is what we'll be having as the numerator and denominator now. All right, so we go on to fill in the value of x being 0. All right, that will be cos 0 over 2. And what is cos 0? Cos 0 is 1. What is the denominator? 2. Do you see right now? we have been able to achieve the final answer. So imagine you are given this question. This is all you need to do to achieve the final answer. I believe everyone can do this. All right, good. Now, this is the first direction you can take. But let's decide to take a different direction, which is good for every student to understand both. So that in case you come across a particular question that L'Hopital may be too tedious and you don't want to sweat over L'Hopital rule, you can go on to try simplification technique. What do you have to do? All you have to do is to simplify your expression. This was your initial expression. So let's go on to try and simplify this. So I have this 1 minus cos x over x squared. What do I want to do right now? Understanding mathematics, I know that I can go on to multiply by 1 plus cos x over 1 plus cos x. This is just, of course, I have told you this before. What I'm doing right here is multiplying by 1, because in the end, this is still the same thing. This and this is the same thing. So what do I get right here? Of course, if you go on to solve this times this is obviously the outcome of difference of 2 square. So I know that this times this will obviously give me 1 square minus cos square x. This is from the theory around difference of 2 square. And what I have as denominator will be this. What I just add, this is x squared times 1 plus cos x. All right. Now, again, I told you yesterday that it is super vital, very, very vital for you to understand your trigonometry if you are going to enjoy calculus. Now, guys, I'm sure you all remember that sine square theta, or sine square x, in this case, let's use sine square x, plus cos square x is equals to 1. So 1 minus cos square x will be equals to what? Sine square x. So I can go on now to write this as sine square x instead of 1 minus cos square x. All right, this will be over x squared 1 plus cos x. You can see the way we're making use of our understanding of around what's the name, trigonometry, to answer these questions. That's very, very, very key. All right, so we have 1 plus cos x. Now look at something here. Look at something very important here. We have something happening here. This is sine x. I can actually split what I have here to be, look at something. I'm sure you agree with me that this, let me just write this and then you'll see what I'm saying. This is sine x over x. Then I have another limit, x tending to 0. I have another sine x over x. Then I have the final one. This is one of the properties of limits multiplied by, let me just put a dot to indicate multiplication, x tending to 0. Then I have 1 over 1 plus cos x. Now look at what I just did. Limit permits you to do this. This is one of the properties around limit, that you can actually split your limit in this form. Look at what we have here. Look at what we have here. Look at what we have here. If you bring these three things together, this is what you have. Because this is sine square x. I splitted sine square x into 2. That's sine x times sine x. This is sine x. This is sine x. I splitted x squared into 2. That's x. That's x. And then I have, of course, there's 1 over 1 plus cos x. Now, if you remember yesterday, we solved this question, this particular question, limit of x tending to 0 of sine x over x. That was one of the last thing we solved yesterday. And if you remember when we solved this, we got our value to be 1. That means this whole thing was equals to 1. We have solved it yesterday. I don't want to waste time solving it. So that's 1 multiplied by 1 multiplied by the limit as x is tending towards 0 of 1 over 1 plus cos x. All right. Now, if you look at this now, you can go on. Of course, all this would go. 1 times 1 is 1. If you look at this, you fix in your value of x as 0, and what do you get? Let's fix in our values for x as 0. That will be 1 over 1 plus cos 0. That will be 1 over 1 plus 1. That will be what? What does this give you finally? This gives me 1 over 2. All right, that's just it. You can see this is the same answer we got yesterday. I'm sorry, just a few minutes ago. And it's just very simple. I want us to not waste time. I want us to solve as many questions as possible. So you will have the opportunity of going back to these videos. So, all right, now let's solve this other question. We have a couple of more questions to solve under limits before we check out of limits and then go to something else. I'll be interested in knowing how much you learned this weekend, and I'm sure you guys are taking good notes. Look at this question. Now, I'm sure at this point, you guys should be more confident when you are approaching any kind of question. I don't expect you to be worried now about the type of questions you have in front of you. So look at this question. How do you solve this? I don't want us to waste much time. You can keep solving. I would move through different ways, and let's see how we're going to get this. Now, I want to use probably one of the fastest way here, which is to go using L'Hopital rule. L'Hopital is quite simple in this for this particular question, but there are other directions you can take that will be much more tedious. Now, look at what we have here. Let's first of all go on to fix in our value of x before we decide to even use L'Hopital rule or not. If you fix in your value of x being 0, this will be sine 5 times 0 minus sine 3 times 0 over 0. And sine 5 times 0 is 0. 0 minus 0 is 0 over 0. Indeterminate form is seen. So at this point, we can go on to solve using L'Hopital rule. How do we use L'Hopital rule right here? We want to find the derivative of both the numerator and the denominator. This is the numerator right here. This is the denominator right here. So let's go on to try and find the derivative of the numerator. What do you get when trying to find the derivative of this? Now, this is very simple. But again, once you don't have that table I've been talking about, you would find this difficult. So there's a part in the table that told you, that gave you the opportunity to solve questions that had sine AX. If you check through your table, you will see a situation where you had sine AX. And if you have sine AX and you're trying to differentiate sine AX, the response will be A cos AX. This is not something that you have to, it's just an identity already. So look at this now. I have this on my table, so I want to use this now. I have sine 5x. So obviously, if you go on to fix in 5 here, this will be sine 5x. That means A here is 5. This will be 5 cos 5x. So simple. That's what you are just going to do to differentiate sine 5x. And for this other side, sine 3x. Sine 3x, that means A is 3 here will be equal to 3 cos 3x. So simple. It's an identity. It's not something you have to rack your brain on. So this will be obviously 5 cos 5x minus 3 cos 3x. All right, that's the derivative of the function we have in the numerator. And then for that of the denominator, this is what we have, 1. I'm sure you agree with that. When you differentiate x, you get 1. Good. So this is a good place we have got into. So what do we want to do next? We want to go further to now find a limit with these new functions. Now this is going to be the numerator now. That will be 5 cos 5x minus 3 cos 3x over 1. All right. So we want to fix in the value of x as 0 now into this expression. So let's try and do that quickly. That will be 5 cos 5 times 0 minus 3 cos 3 times 0 over 1. So what we have here is 5 cos 0, because 5 times 0 is 0, and minus 3 cos 0, because 3 times 0 is 0. And we have over 1. What is cos 0? Cos 0 is 1. So that will be 5 times 1 minus 3 times 1 over 1. That will be 2 over 1. That will be 2. You see how L'Hopital was able to give us our solution in no time at all. Now, some other people can pass through a different route, and just for the sake of flexibility and because I want you to be very versatile in anything calculus, I don't want you to just be seeking for, you may not see exactly this kind of question, or you may see something similar but may have some ingredient that may make it a bit more complex. So you have to be ready for any sort of thing, and that's why I want to use the simplification means. Even one thing I'm going to do is I'm going to simplify this in such a way that it gets more complex, and then I will still use L'Hopital. Let me first decide to simplify the normal way and not using L'Hopital, and let's see how we get the final answer. Now, first of all, look at what we have here. This is very important. Look at what we have here. Sine 5x minus sine 3x. Now, imagine you wanted to simplify. One thing you need to recognize is that you have an identity under trigonometry that resonates with what we have here. This is what we call the sum and difference identity. And what does the sum and difference identity tell you in a case like this? When you have, if you remember when I gave you this is when you have sine c plus d over 2. Sorry, for this one, you will have it as sine c minus d. And you'll be having cos don't know if you may remember this. This is one of your identities. So when you have the sum and difference identity, this is how you apply. So when you have a case like this being C, this being D, this being C, this being D, this would be obviously 2 sine 5x minus 3x over 2 cos 5x plus 3x over 2. This would be 2 sine 2x over 2 cos 8x over 2. This would be 2 sine x cos 4x. I told you about the need for you having good knowledge in trigonometry for you to enjoy calculus, especially when you are dealing with circular functions, which is a very examinable aspect of calculus. Now, this means that instead of writing sine 5x minus 3x, this is what I'll be substituting it as now. So I can have it now as limit, as x was tending to 0, 2 sine x cos 4x over x. All right? That's just flowing with my normal substituting this for this. Now, let's go home further now and do something. I told you already that under limit, there is one of the properties of limit. When you have something like this, you can go on to split this. It's permitted. I splitted the last question, and I'm sure you guys saw how I did the last one. So I can go on to split this. That means I'm okay with doing it like this, where I can write 2 sine x over x dot limit of x tending to 0 cos 4x. Look at what I just did. So I splitted this whole fractional function into 2 different parts, and I maintained the limit with them. That's permitted in under limits. So when you see something like this now, I can now go on now to try and resolve this a bit further, right? Now, what do you see? I can see a 2 here. Let me drive these 2 outside. Let me drive these 2 outside. Because of space, I will just automatically remove this, and I'm still okay with, I can still do it like this. It's still permitted. So rather than having 2 here, I brought the 2 here. All right, that's permitted also. These are some of the things that you need to or understand the properties around limits. Now, look at what we have here. We did this already yesterday. Of course, it's not very hard at all. We did this already yesterday. Limit of x tends to 0 of sine x over x. We did it yesterday and we have used it today. This is giving you 1, all right? So this is 2 times 1. This whole thing is 1. Then let's try and solve for this. As x is tending to 0, what do we have? We have, let's put x as 0. That will be 4 times 0. That will be cos 0. That will be 1. So we have 2 times 1 times 1, and that's 2. Do you see that? How we're able to solve using simplification. So this is a different technique, but we're getting the same answer. So you can use L'Hopital, which we used. We used L'Hopital initially. We got 2 as our answer. We're using simplification, and using my simplification, I needed to understand the identities around trigonometry, which I used. I was able to resolve sine 5x minus sine 3x using my sum and difference identity. I got this. Now I went on to split my limits because this is permitted. All these can be splitted. I brought this on one side. I left this other one on this other side. I brought the 2 here, and I discovered that, of course, this, if you want us to still solve this, we don't need to because we had this yesterday. The limit of x tends to 0 of sine x over x is 1. And then we went on to fix x as 0 here. We got it as 1. 2 times 1 times 1, that's 2. Now, this last method I want to use is actually from here. You know, we decided to simplify. We didn't use L'Hopital. Look at what I did. When we got here, after I simplified the numerator, I got it here. I went on to use normal simplification. I just simplified it, used my theory around limits, and got my answer. But let me now, because I want to test you guys' ability, I want you people to, from this place now, from this particular place, what we have here, I want you to quickly use L'Hopital now to solve this. Use L'Hopital to solve this. And the reason why I'm saying that is because I want you to get more, get your hands on more questions like this. Circular function, you can see what we have here. So I want you to be able to solve this. So can you try and solve that using circular function, and let's see how you're going to get your answer. So let me see people that have been following. Try and solve this using L'Hopital. So of course, I hope you understand that in your question, they may just say using L'Hopital, solve this question, a theory question, and they want you to go on because using L'Hopital will test your ability to differentiate the circular function, and also to, if you understand the theorem around L'Hopital. So can you quickly try and use L'Hopital to solve this? Of course, I'll be doing mine right here. So that means I'm just going to say my f of x, that's my numerator, is 2 sine x cos 4x, all right? And my gx, which is my denominator, is x, all right? Fine. So using L'Hopital, I want to go on to find the derivative of both the numerator and the denominator. So I have numerator of the derivative of this, which is probably going to be the most testy part. So look at what I want to do right here now. I want to differentiate this whole thing, guys. This is testing. Let's differentiate it. Of course, g of x is quite very simple. The g of x is just 1. My answer for g of x is 1. So I'm sure everybody can do that one. But I'm talking about this f of x now. Can you attempt this? What's the derivative of the numerator? Of course, I want us to solve it together. That's why I'm trying to bring it to your attention. All right. Now, when you see something like this, this is one of the things I talked about yesterday. This is a perfect example of where you'll be needing to use what we call the product rule. When you see a question like this, this is, of course, the product of two different this is obviously a product of two different expressions. This is 2 sine x multiplied by cos x. All right. So what I want to do now is I want to split these two expressions into 2 parts. This will be the first. This will be the second. I'm going to call this first part u. I'm going to call the second part v. And this is my product rule. This is what product rule said. Product rule said that when you have a situation like this where two things are being multiplied together and you are trying to differentiate them, especially in a case like this, now you can see this is a perfect example. Two things are being multiplied together, this times this. How do you solve this? Just go on to have just go on to, first of all, split it the way I've done it. Call one u, call the other one v, and then apply those two things into this expression. U the v over the x plus v the u over the x. Very simple, right? So now I know my u, I know my v, but I do not know the v over the x. So what I want to, so look at it this way now. My u is 2 sine x. My v is what? Cos 4x. All right. But I need to go on to find the u over the x now. And then also the v over the x. So guys, what is the u over the x? This is another example of one of those things that you need to have your table handy. When you differentiate sine x, you get cos x, right? So the u over the x obviously will be 2 cos x. Very simple. That's this is not something you have to sweat over. This is on your table. Differentiate sine x, you get cos x. All right. What is the v over the x? The v over the x, of course, there's another part on your table that said if you have cos ax, it said you are going to get what? Minus a sine ax. That was what he said, your table. Minus a sine ax. This is what your table said. So look at this, is a perfect example now. I have cos 4x. So obviously this will be minus 4 according to this identity. He said whatever your a is, minus of it. Minus 4 sine 4x. So this is not something anybody is manipulating. It's just an identity. You just need to know it. All right. Good. Now, we have gotten our u and v and the u over the x and the v over the x. So what I want to do next is to fill all this into this product rule. And what do we do now? This is my u. I have 2 sine x multiplied by the v over the x. That's minus 4 sine 4x plus v. That's cos 4x. Then multiplied by the u over the x. That's 2 cos x. Now, this is your answer to the derivative of your numerator. Look at the answer right here. So guys, imagine they gave you this in anything you have to do, and they said differentiate 2 sine x cos 4x. This is the answer. Now, of course, you can obviously break this further. That's something you can easily see, because in this case, you are multiplying these two things together. So this will be minus 8. 2 times minus 4 is minus 8. This will be sine x, then sine 4x, plus this will be 2 cos x, then cos 4x. So this is the final answer for your derivative here. Minus 8 sine x, sine 4x, plus 2 cos x, cos 4x. That's your answer right there. So can you imagine that? That is just the numerator. So what you want to do next now is to put those things back into your expression. So now you want to have, permit me to do this, please. I will just, because of time and space, I will clean this up. You know my g of x was this, so I'll just write it like this. Limit of x tending to 0. I'll write all this over 1. I'm sure you understand what I'm doing. So this is our numerator, the differentiation of our numerator, and this is the 1 was what we got when we differentiated the denominator, which was x. Now, what we need to do now is to go on to fill in the values for x as 0. So go on to do this now. You'll be having this place will be sine 0. Permit me to do that also. This place will be sine 4 times 0, and this place will be cos 0. And this one will be cos 4 times 0. So obviously sine 0 is 0, so all this turns to 0. So I have 0 plus 2 times cos 0 is 1. This will be cos 0, which is also 1. 0 plus 2, because 2 times 1 is 2. And this final answer gave me 2. So guys, can you see how we went on using about 3 different techniques and we are arriving at the same answer? Do you see how interesting calculus is? It's very, very simple. There's nothing, you have no need to fear this at all. All you need to do is to just follow the steps that you've already known, and you can never go wrong. So guys, don't forget we are on speed tonight because we have a lot to cover, and don't forget your exam is very close, and I'm expecting that all this should lead to lot of great success in the coming exam. So I want you guys to please flow along and make sure you are working with us. Make sure you are making an attempt. When you see a question, make an attempt on it. That's how you get more confidence. Now look at this example. We have x tending to pi over 3. A bit different, right? And we have it as sec x minus tan x. This was the question you were given. And you're told to find the limit of this. All right? You are told to find the limit of this. So how do you find the limit of this function when you have your x tending to pi over 3? Now, again, I told you, you need to have knowledge around trigonometry for you to understand calculus properly. If you do not understand what pi over 3 means, and you don't even understand what pi means, you'll be having some issues. All right? When you're dealing with angles and you see the symbol pi, it actually means radian. So now let's go on to solve this question. We have sec x minus tan x. What do we got to do? What are we going to do here? If you go on to just fill in your values for x as if you go on to fill in your values for x as pi over 3, one of the major issues you may face here is that you do not know, you do not have sec on your calculator. So what I will advise is to go on to try and remember your trigonometric functions and try to simplify this a bit further. And how can you simplify this? Sec x is obviously 1 over sine x. So you have 1 over cos x. So 1 over cos x minus sine x over cos x. So we have at least simplified a bit. So now I can see this is possible for us to have LCM, because I can see cos x and cos x are playing at the same time in the denominator. So I just find the LCM of that. That will be cos x, and that will be 1 minus what? Sine x. All right. So look at all these things are using my knowledge of trigonometry. If you do not know all these things, you would probably get hooked at the initial stage. So this is why you need to go back to rehearse your trigonometry identity. So now that I've simplified a bit to a point where I can easily use my calculator, I can go on now to fill in my values for x. So I have sine pi over 3 over cos pi over 3. All right. Now, the question now, when you have sine pi over 3 being written, for somebody that is ignorant and do not understand trigonometry, the person is looking at this and is wondering what is pi. If you don't care what the person wants to even put in 3.142, and that will be so wrong. Pi is not 3.142 here. Pi is 180 degree. All right. Pi is 180 degree. So that will be 180 over 3. That will be 60. So that means what I can essentially write here is the limit of x tending towards pi over 3 will be, of course, I do not need to write this again because I'm solving already. Now I'm having 1 minus sine 60 over cos 60. All right. What is sine 60? If you go home to draw your special triangles, you would be able to get this much more easily. I don't think I want to do much of that because I know that's under trigonometry, and I believe everybody should be familiar with those things. You draw your special triangles, you don't have to get a decimal point. You can easily write this as pi, so 3 over 2. That's sine 60. Whereas your cos 60 will be 1 over 2. All these are something you can get from your special triangles. So if you go on to try and solve this, you will be having, of course, you want to find the LCM because this is over 1. You want to find this as 2, and this will be 2 minus 3 over, then we have 1 over 2 here. So it's more like you have, I'm sure you can follow what's going on here. I found the LCM of what is the numerator, and that was what I got, 2 minus 3 over 2. Then the numerator is 1 over 2. So I have 2 minus 3 over 2. Then I can say divided by 1 over 2 because this is all division. So I don't need to waste time here. I can clean this up and make the reciprocal of this. And then this cancels this. And my final answer will be what? 2 minus 3. Now, can you see that in this case now, we did not get an indeterminate form. We did not get 0 over 0. So as I said already, you don't always get that kind of form. In some cases, you get answers that are perfect like this. So imagine we got, after we fill in our x as pi over 3, imagine we got 0 over 0. That's where we will then go on to be trying to find it using probably L'Hopital rule or the other method. So guys, I'm sure you can flow with all what we're doing. And I'm sure you guys have gotten better, which is what we are here for, right? Now, we are getting closer to the end of limits. Just in a few moments now, I'll be out of here. So we're getting closer. Now we're going into another interesting part where questions, those are places where people, a lot of students have issues, and they always bring questions out from there because it's very, very examinable, where they will tell you to differentiate using first principle. In the case where they told you to differentiate using first principle, they could tell you to differentiate y equals to x squared, and they say differentiate y equals to x squared. And obviously, you can easily see that the answer to y equals to x squared is 2x. And you feel like just writing the answer as 2x as the answer because you could do that easily. But if they told you to do this using first principle, you must do it using first principle. If not, you will not even get any mark at all. So, yeah, so now look at what we have here. We have this question. I want you to make an attempt on this. Before getting to first principle, we will be we'll be talking about continuity in a moment so that at least we can be sure of everyone knowing how to solve that also. Then we'll get into first principle. Now look at this question. Let me see what you do around this. We have this question. It's similar to the one we just solved. In this case, now x was tending towards pi over 6. And we have sine 2x over sine x tan x. So now I would love you to make an attempt to this very quickly. How do you solve this? One of the things I want you to always understand is that if you don't understand trigonometry very well, you'll be having lots of issues with calculus, because now there is something you're going to do to this question that is going to make your work quite very easy. But if you are having issues with that identity in trigonometry, it will look very hard to solve it. That's why I would love you to go back and rehearse your identities. Now, if you are dealing with trigonometry, I'm sure you remember that what you have here, sine 2x, it's also the same thing as 2 sine x cos x. So I can have it like this. I can simplify to this. All right. Can you see what just a simple knowledge of double angle in trigonometry? Can you see how it gave you advances with your calculus? So because I understood that sine 2x is equals to this, do you see what happens once you are able to apply that identity? it brings a lot of understanding. It brings a lot of clarity. So I don't think you need to start asking that. You can obviously cancel sine x. The sine x can cancel sine x here. So we can have this canceling this. Of course, that's very much permitted. Now, that means I will be having the limit of x tending to pi over 6. Now I'll be having 2 cos x over tan x. Could you see that? Now, I know also this doesn't make too much sense. It makes sense, but I know that I can break this further because I know something in trigonometry. I know that my tan x is equals to sine x over cos x. So I want to do everything possible to see how to eliminate all the bogusses in my work. So I have 2 cos x over sine x over cos x. That is my identity for tan x, which I know nobody is arguing about. So if I go on to try and solve this, let me just try and solve this here. We have 2 cos x, okay, divided by sine x over cos x. That will obviously be times, then we make the reciprocal of it. That will be cos x over sine x. So obviously, I'm going to be having the limit as x was tending towards pi over 6. I'll be having 2 cos square x over sine x. All right. Now, I can now go on now that I have simplified this in such a way that it's far more easy now to fill in my values of pi over 6 now. Now, I want to go on now to fill in those values. That will be 2 cos square pi over 6 over sine pi over 6. All right. I told you already, this is the first thing you want to do. You want to fill in your values inside. Now, we have filled in this value inside, but don't forget, what is your pi? Pi is what? 180. So this is 2 cos square 180 over 6. That will be cos square 30 over sine 180 over 6. That's sine 30. And you already know that your cos 30, because this will be the same thing as is like writing 2 cos 30 all square over sine 30. If you understand the meaning of cos square 30, cos square 30 means cos 30 all square. All right. Now you see we have what is my cos 30? My cos 30 using your special hand triangle. Those of you, if you have issues with trigonometry, it's going to affect you greatly in calculus. All these things I'm writing, the next thing I want to write now, I want to write sod 3 over 2. And someone will be there wondering, how did they get sod 3 over 2? It's just for my special triangles in trigonometry. All right. And my sine 30, I can write that as 1 over 2 because it's also in my special triangles. So if I go on to make to try and solve this, of course, this would be what? This would be sod 3. This would be 2 multiplied by 3 over 4 over 1 over 2. This would be 1. This would be 2. That's 3 over 2 divided by 1 over 2. That'll be 3 over 2 times 2 over 1. This cancels this. That will be 3. I'm sure you guys can see that. This is 1 over 2 right here. 1 over 2. So you see exactly how this thing works. For those of you that probably everything we did here is just number one. We started by saying, what was my sine 2x? My sine 2x is 2 sine x cos x by identity in trigonometry. Double angle. This is double angle I'm applying here. Double angle brought this out. All right. This is double angle achieving this. Now we're done with that. We were able to cancel sine x and sine x. We add the remnant as this. So what did I do next? I brought my tan x as sine x over cos x, right? Then I went on to try and simplify it. Trying to simplify it, I got it as 2 cos square x over sine x. Then at this point now, it looked much better to fill in my values for x as pi over 6. I filled it in as pi over 6. Of course, I remember that pi is 180. Pi is 180 degree. So 180 over 6 is 30, and this is 30. So I was able to get this. Of course, somebody is talking about following a different method. You can follow any method as long as it's mathematical. What really matters is that you are being mathematical in all your approaches. I think there was one question we solved some minutes back now where I used 3 different methods and we got the same answer. So of course, imagine I just used one of the methods. You may have used the second one. Someone else may have used the third one. Those don't matter as much as you are following the right pathway. But one thing I would just tell you is that if you are told to use a particular rule, for instance, using L'Hopital rule, you must follow L'Hopital rule. So all I went on to do was to fill in my cos 30, which I knew was pi 3 over 2. So 3 over 2, and then sin 30 as 1 over 2. I went on to simplify this mathematically. I got my answer to be 3. So this is very, I believe those of you that probably you were having some issues, you are probably getting much better now. That's the key. You have to solve more questions, Now this will be the second to the last question we'll be solving around limits. So if you have not gotten it at this point, I would advise you. Okay, I think this will be the last question we'll be solving. So look at this question and let's see how you're going to go about it. I would love you to use both the L'Hopital rule and the simplification rule. So we have the limit. In this case, x was tending to 1. And we have the sod of what? We have the sod of 5x minus 4 minus sod x, rather not sod 2, sod x. And we have over x minus 1. This is the question. All right. This is the question. So we have this question right in front of us. We are to find the limit as x was tending towards 1. So guys, put your hand on this. This is the last question on this aspect of limit before we get into, we want to get into first principle so that you guys can at least have a good idea. We obviously will not be able to delve very deep into first principle tonight, but we want to get into the basics around it. So, and then we would at least be sure that you know what to do. So let's use both L'Hopital and the normal simplification technique. So which one do you feel you want to use first? This is something I want you to be very calm when trying to solve. So let me try to simplify first, and then we'll go on to use L'Hopital. So you can go on wherever you are. You can go on to use whatever method you want to use. So I want to go on to simplify. The best thing is for us to work together. So you can be doing yours while I'm doing mine. And then if you get hooked, you can obviously check through on where you made your mistake. So the very first thing I want to do right here, when I see a question like this, whenever you see questions like this, the best thing to always do in many cases is to multiply by the conjugate of the complex situation. This is the complex part of this thing, which I want to decomplex. Majorly, I want to decomplex this. So one of the best way of decomplexing this is to multiply by the conjugate, which will be this. And you're not just going to multiply by, you have to rationalize, if you understand what I mean. You have to do this in such a way that it's not going to be like you are trying to cheat. So what I just did here was like multiplying by 1. But of course, I'm going to use what I'm doing right here to change the form. That's exactly what I want to do. All right. So look at what we have right here now. We have a very more, better looks, because now I can see that I can this and this of course, they are looking like difference of two square. For those of you that probably you've not been able to follow me when I'm saying difference of two square, a square minus b square under algebra is a plus b, a minus b. So if you look at this now, this is like a minus b, this is like a plus b. So obviously, it's not wrong if I go on to write all these things as a square. That means this one, all this one square minus all this square. So it's not wrong if I wrote this as square root of 5x minus 4 square minus square root of x square. Difference of two square. Since this is the case on the numerator, then this can also be the case. I'm still right. This is just algebra. So this will be all over, of course, everything we have beneath. And whatever we have beneath is all this. We have x minus 1 here. We have square root of 5x minus 4 as this first part here. Then we have we have this together. We have plus square root of x. All right, this is the denominator. Of course, we are still having our limit of x tending to 1. Yeah. So what do you want to do next? You can obviously simplify this because the square will deal with this. So I'll be having 5x minus 4 minus x because the square will deal with this also. All right. So this is what we have as the numerator, while our denominator still remains the same. So our denominator remains as whatever we have here, x minus 1, square root of 5x minus 4 plus square root of x. All right. Of course, the limit is still present here. So what do we do next? 5x minus x, now this will be 4x. 4x minus 4. I'm sure you know this can be written as 4x minus 4, which can also be factorized. You can factorize 4 out and have it as 4 into x minus 1. All I'm doing here is just basic mathematics, all right? Now, what do we have next? So we have our denominator as the same. We have x minus 1. I'm not seeing anything feasible under the denominator apart from just rewriting it, which is not a bad idea because don't forget, what I'm trying to do here is just to simplify before I fill in my value of x as 1 because my limit was x tending to 1. So I just want to dress it up in such a way that it looks nice. And then when I'm done making it look nice, then I'm okay with chasing filling my x as 1. All right. Now, look at what you can see. I'm sure some of you are already seeing it because this is very obvious. You can see x minus 1 here. You can see x minus 1 here. So this can obviously cancel this. So I'm left with this. So I told you already it's nice and better if I wrote it like this. Now, instead of writing 4, normally I could write 4 over all this as the next thing. But I want to bring this 4 outside. So I have it as 4. It's still okay. This is still permitted. So I will now have 1 over. Now I have the old denominator as 5x minus 4 plus square root of x. All right. This is, you can see how carefully I'm ensuring that I'm moving through everything step by step. So now at this point now, I'm okay now with filling in my values for x as 1. So let me go and fill in the value. That means I want to take the limits now. So I go on to have 4. Now I have 1 over, all right, this will be square root of, this is 1 over, I have square root of, now this is 5 times 1 minus 4 plus square root of 1. This is over. So this is my denominator, and I'm sure you can relate to what I'm doing. So look at what's going on here. This 5 times 1, this 5 minus 4, that's 1. That's square root of 1. I'm sure you agree with me. Square root of 1 is 1, right? So that will be 4 times 1 over square root of 1, which is 1, plus square root of 1, which is 1. All right? I'm sure you can see what's going on there. So this, sorry, let me use this place now. I believe you can relate. This will be 4 into bracket 1 over 2. And that will be 2 will go here 1, 2 will go here 2. The final answer give you the answer of 2. Does it make sense? How many of you were able to flow with what I did? How many of you understood exactly what went on here? No big deal at all, just simple stuff. Very simple and straightforward. We're just following mathematical principles and we're getting our answers. Now, one thing I want us to do next now is to go on. This was using simplification means, which of course, we have been able to get a final answer. So we got our answer to be 2 when we use simplification. Let me just try and run through this because some people are probably trying to still understand it. Look at it now. This was the question they gave me. They said the limit of x as a limit of this function as x was tending to 1. They gave me this. All right, I want to use simplification. I'm not using L'Hopital or anything. I want to use simplification. Now, by the way, if you are wondering why I could use L'Hopital here, I will show you very soon. But it's very possible for you to use L'Hopital because you will get an indeterminate form. If you fill in x as 1, I will show it to you very soon. You will get an indeterminate form. But now I want to use simplification method. All right. Yeah, I'm going to come again for those of you interested. So this was the question, what we have here. Square root of 5x minus 4 minus square root of x over x minus 1. So I want to simplify this. Simplification means I want to bring it in such a way that I can easily relate to it because all this doesn't look so much relatable. So one of the best way of solving situations like this is to try and change the form, because you can change the form easily when you have things like this by just doing this operation in mathematics. This operation is very useful when you are dealing with mathematics. One of the things going on now is that you see, I can see that this is something here. I know that if this and this, what I have here and what I have here come together, look at what happened. I'll be having this because I know my difference of 2 square. So, but I cannot just say I'm multiplying the numerator by just this alone. That will be wrong. So I have to use a technique in mathematics where I'm multiplying by this over this. Obviously, if you ask me what have I done here, I just multiplied by 1, which is still the same thing. But of course, this will help me to be able to change the form of this, my function. Now that I have done this, I used a theory in mathematics called difference of 2 square. This is just how simple difference of 2 square is. It said when you have 2 squares, a square minus b square, it's equals to a plus b and a minus b. That's perfect. That's something that has been established already. So now we have this established. Look at what we have here. Let's take this as a. Let's take this as b. You can see this is a minus b. This is a plus b. So obviously, a plus b, a minus b is happening here. So I can bring all this to be a square minus b square, which is what I just did. So I change this whole numerator to look like what we have here now. Since I can see that this all conform to this, so I can say this is obviously equals to this. I can say what I have here is obviously equals to this. So this is this. So I can write it as a square minus b square. Difference of 2 square, it will give me this back. That's just the principle in mathematics I'm using right there. Now, so I was able to bring all this numerator to just this, what I have right here. Now, the numerator remains the same, nothing changed. I just put x minus 1, I put this, look at it. These are together, by the way. So this is it right here. All this is here, and all this is here. All I just did was bring the numerator using difference of 2 square. Good. Now, because I can see, you know what squares and square roots are in mathematics. I have square of a square root number. So obviously, this square obviously cancels this square root, and this square obviously cancels this square root as per mathematics functions and operations. So I'll be left with 5x minus 4, which is here, and I'll be left with x alone, which is here. Good. Now, you want to solve this. You have 5x minus 4 minus x. 5x minus 1 minus x. This is 5x. If you want to solve this, this will obviously just be like, say, 5x minus 4, then minus x. That will be 5x minus x. That will be 4x. And this is minus 4. So all this resulted into 4x minus 4. Now, I'm sure you agree with me that 4x minus 4 is the same thing as factorizing 4 and making it x minus 1. That was all I just came here to do. Don't forget, the denominator is still the same. I have not changed anything about the denominator. It's still the same thing. What I've been carrying here is what I carried here also. So I changed this my numerator now because it was 4x minus 4. I changed it to 4 into bracket x minus 1. Now, once I did that now, I saw that x minus 1 was here, x minus 1 was here. So obviously, I could cancel both of them out. So I cancel this out. I was left with 4 over this. Now, I could go on to, if I had enough space here, I could go on to first write this as limit of x tending to 1, 4 over what I have here. But because of time, I just shifted this 4 out. And then when I shift 4 out, I'm left with just 1 on the numerator, which is what I have right here. Then the denominator now is left with only this side of things because x minus 1 has been cancelled. So this is what I have right here. Now, at this junction now, it's very fine for me to now go on now to use my limit of as x was tending to 1. All right. So if x is tending to 1, I can fill in my values for x as 1. So I have 5 times 1 minus 4. 5 times 1 is 5. 5 minus 4 is 1. So that will be 5 minus 4. That's square root of 5 minus 4. That's square root of 1. What's square root of 1? Square root of 1 is 1. That's why all this square root of this thing here resulted to 1. What is x? X was 1. So square root of 1 also. Square root of 1 is 1. So I have 1 over 1 plus 1. That's 1 over 2. That's 4 times 1 over 2, which is 2. Does it make sense now? Good. Now, we want to go on now to use L'Hopital rule now, because that's something you know, it's possible they just give you this question and they don't even want you to use any method of your choice. They want you to compulsorily use L'Hopital rule. So let's go on to examine this using L'Hopital rule. By the way, guys, did you understand it better now? Those of you that asked, why is our thumbs up very low this night? Have you guys forgotten to always punch the thumbs up button? Okay, so now we have L'Hopital rule. Very, very important. I want you to always understand this method. I want you to be so familiar with it that you're not any way confused. All right. Now look at something going on right here. First thing and foremost that you want to do when you have a question, I've told you before, apply the x as 1. So put in x as 1 here. This will be 5 times 1 minus 4 minus square root of 1 over 1 minus 1. I'm fixing x as 1. All right. Now, this will be what? Square root of 5 minus 4 minus square root of 1 over 0. This will be 5 minus 4 is 1. 1 minus square root of 1 over 0. Square root of 1 is 1. That will be 1 minus 1 over 0. 1 minus 1 is 0. 0 over 0. Can you see right now? We have gotten to what we call the indeterminate form. Now, this is when you determine to use L'Hopital rule. I've told you already, don't just jump into using L'Hopital rule. Ensure you first try out the limit. After you try out the limit, then you are able to now say if you're going to use L'Hopital or not. The only reason why you use L'Hopital is if you have indeterminate form. So good, we've seen that this arrived at an indeterminate form. So let's go on now to use L'Hopital rule. Quite simple. Now, what does L'Hopital rule say? So we have to define our functions. Numerator, we call it function f of x. It's sod 5x minus 4 minus sod x. And what is our gx? Our gx is x minus 1. That's the first step under L'Hopital rule, right? Now, the next thing you want to do now is that you want to go on to find the derivative of both your numerator and your denominator. What is your derivative of course, the easier one to find is that of your denominator. The derivative of g of x here is just 1, because when you differentiate x minus 1, you just get 1. I'm sure all those things are clearer to everyone. I don't think anybody should have any issue in differentiating. So, but for this one, how do you do this? How do you do this derivative? Now, this is one of the things that I believe will test our understanding of quotient rule. All right. Sorry, chain rule. So look at what we have here. We have this. I want to find the derivative of x. Now, you cannot just go on to just solve this. You have to remember some things. Let me rewrite my f of x in such a way that will make it easier to relate with and make it much more ready for differentiation. If I have something like this, I'm sure you agree with me that this is the same thing as fx minus 4 raised to power 1 over 2 minus x raised to power 1 over 2. I'm sure everybody here agrees with this, that my function f of x is still the same thing as this, because when you have square root of something, it's the same thing as writing that whole thing over 1 over 2. That's just basic mathematics. So what do we want to do now next? We want to go on now to, let me start by saying something. You cannot go on now to just say, I want to differentiate this directly. You can differentiate this one directly because this is a simple expression. But this expression is not simple. If it was just 5x raised to power half, it's a different thing. But this is a whole compound expression raised to power 1 over 2. So this is where you have to use what we call chain rule. You cannot use, you cannot do this straight up. But I can do this one straight up. Okay, so this can still follow your normal, this x 1 over 2 can still follow the normal procedure. What we have here cannot follow the normal procedure because look at this is a compound expression. This raised to power 1 over 2, you cannot just go on to say 1 over 2 times this then minus 1 here. It cannot work that way. But this one can work that because this is a simple expression. So what do we want to do? Let's do the simple expression first and let's see how this one will go. It's the same procedure when you have to differentiate something like this. If it's just a simple one like this, what you want to do is to say you want multiply, of course you multiply the power times the coefficient. Coefficient here is 1, so that'll be half times 1 is half, then x raised to power the power minus 1. So this would be 1 over 2 x raised to power minus 1 over 2. This is the answer. Of course, it can be written in a better way. If I write it as 1 over 2, now this x raised to power minus 1 over 2 can be written as 1 over x raised to power 1 over 2. I hope nobody is lost in what I'm doing. I'm hoping so. Then you can write it as 1 over 2 times 1 over square root of x. This will be 1 over 2 square root of x. So the derivative of this part, this is the answer. Hope nobody was lost. Hope everybody could follow me what I was saying here. I want to be sure nobody is getting it wrong at all. So what I just did was the normal thing. You know, when you have a situation like this, you say this times the coefficient. That will be, in this case, that will be half. Then x raised to power, you subtract 1 from the power. You follow that same procedure. When I subtracted 1 from the power, I got minus 1 over 2. Right? Now, this is 1 over 2 x raised to power minus 1 over 2. This is the answer. So I can reformat it. I can put it in a different form. And what's that different form? This is what I have here. Now, instead of writing x raised to power minus 1 over 2, I know that this minus makes it 1 over x raised to power 1 over 2. I'm sure you know all these laws around indices. So this is 1 over 2 times 1 over x raised to power 1 over 2. Now, this whole thing, this x raised to power 1 over 2 can be written as square root of x. So that's 1 over 2 times 1 over square root of x. And that's what gives me what I have right here. All right. So now, this is just the answer for this simple one. But this one, you cannot do it that way. So you can do this one that way. You have gotten the answer. This answer is correct for this one. So for this one, we have to use what we call chain rule. And this will bring us to the explanation around chain rule. So when you have something like this, if you call this, you know, when you have something that is a compound expression, for instance, let me give you some other instances. Let's say I had even 5x minus 4 raised to power 2 or raised to power 3 or 3x minus 5 raised to power 5 or anything. When you have expressions like this, you cannot just go on to just use this basic way. You have to use what we call chain rule under differentiation. What is chain rule? What chain rule does is that the first thing you want to do is to represent whatever is inside your bracket. You want to represent it with any letter you want. The most one I'll be using here is U. So I'm going to use this as U. So let me call this Y. So I want to say Y equals to U raised to power 1 over 2. I'm calling my f of x Y because it's easier to work that way. I'm calling my f of x my function Y. And I'm calling what my 5x minus 4, I'm calling it U. All I just did was we represent these things with different alphabet. So f of x is Y and 5x minus 4 is U. So I can write it here that U equals to 5x minus 4. I'm sure everybody agrees with that. There's nothing different from what I've been saying here. Is what I just did is something I believe everybody can relate to. So all you want to do, what is the theory around what's the theory around chain rule? Now, it's like you had, look at what we had before. Let's y, f of x was y. We had f of x equals to 5x minus 4 raised to power 1 over 2. This was what we had called f of x y. I'm sure you know it's still the same thing. So we wanted to find the y over the x. We wanted to differentiate this y. We wanted to find the y over the x. That was what we wanted to find. This was where the problem was. We had y being this and wanted to differentiate y. So what chain rule said is that if you have a solution like this, the y over the x will be equals to the y over the u dot the u over the x. That's chain rule. What I just wrote for you is chain rule. Chain rule essentially is the y over the u dot the u over the x. If you can look at even the logic around this, you can see that the u makes it the y over the x. So that's an easy way to understand this. But you have to solve these things. So in a case like this now, I want to go on, look at what I'm looking for. I want to find the y over the x. This is what I'm looking for, the y over the x, which means I was doing this with respect to x. That's meaning of the y over the x. So I want to differentiate the function y with respect to x, right? Now, how do I go about that? What I need to do is, first of all, I want to differentiate, after doing this, I want to differentiate my y with respect to u. So I want to find the y over the u, which is, you can see it right here. I need to find the y over the u, and I also need to find the u over the x. Look at them right here. So I need to go on now to find the y over the u, and I also need to go on to find the u over the x. All right. So these are the two things I want to go and find now. If I say I should find the u over the x here, everybody knows what the u over the x is. That means I want to differentiate this function with respect to x. Of course, the u over the x will obviously just be 5, because if I differentiate this function, I'll just get 5. That's perfect. I've gotten that. All right. And the y over the u looks like this. Looks like this thing. You can see. Of course, I can go on to do this again afresh, but I'm sure everybody here can understand that it's better to I can just make use of this one I've done already. So the u raised to power 1 over 2. If I want to differentiate this function with respect to u, I will follow this whole process. This is a simple expression. So this would be the basic way, where I'll just say half times the coefficient. That will be half times u, then raised to power half minus 1. Of course, following the same process. So that means I will arrive at this. The difference will only be that I'll be having square root of u instead of square root of x. So the y over the u will be obviously 1 over 2 square root of u. All right. So that means we have been able to get our dy over du and our du over dx. So obviously, applying this to chain rule now, the y over du is what? The y over du is 1 over 2 square root of u. And what is the u over dx? 5. You see how perfect this is. So this means already that I have gotten my dy over dx. I've been able to successfully differentiate this function. Now, what am I going to say is my answer when I differentiated this function? Of course, what I've gotten is good, but it's not yet perfect. What I wrote here is good. That means I'm saying now that the y over the x, which is this, is equals to 5 over, that's 1 times 5, 5 over 2 square root of u. That's what the denominator is. Now, I don't need to leave it in this form because obviously I know what my u was. My u was 5x minus 4. So I can go on to substitute that inside here. So I'll just put u as 5x minus 4. And this is the answer. So if you are asked to differentiate this whole thing now, this is the answer. The answer for differentiating 5x minus 4 raised to power 1 over 2. So that's almost so that's going to be this is going to be like the new function you're going to have, and then you will be able to now go on and examine this using your limits. So now go on how to, of course, we're dealing with L'Hopital, don't forget. And of course, if you're having some issues, you can go back out and you can go out and come back again. It's possibly just the network. So now look at, this is the derivative for the top. This is the derivative for the denominator. So what you want to do now is to, of course, we are using L'Hopital here. You can now go on to find your, you can go on to put in your values for x. Your x is tending towards, your x is tending towards 1. So you can go on to fill in x as 1 now. And let's see what you're going to get right there. So when you fill in your x as 1, we have our x tending to 1. The limits as x is tending towards 0, we have 5 over, then we have 2 square root of 5 times 1 minus 4 minus 1 over 2 square root of x. So in this case, of course, x now is 1. So in this case, we are having, we don't have to have this anymore. So in this case, we have 5 over 2 square root of 5 minus 4 minus 1 over 2 square root of 1. This will be 5 over 2 square root of 1 minus 1 over 2 square root of 1. Square root of 1 is 1, square root of 1 is 1. This will be 5 over 2 minus 1 over 2. And this will be what? 5 minus 1. Now will be 4 over 2. And this will be 2. So do you see the whole process using L'Hopital rule? Very simple. The major work was in finding the derivative of the numerator. The numerator was quite easy, but the numerator was the tedious work. So once you are able to solve the derivative, all you need to do then is to fill in your values for your x. Of course, it was tending towards 1. You fill in x as 1, and you can see how we got the same answer as the other one we got. All right. All right. So this will bring us to the theory around continuity. Let's run there quickly. I want us to ensure we are done with that also before, so that you can be perfect in everything calculus. So now, I believe with all these many questions we have solved, everyone should be able to solve questions around, we should be able to solve questions around L'Hopital rule or anything limits. I don't expect people to have issues with limits anymore, because this is basic already. This should be basic to us already. We're still on calculus, and let's talk about continuity. So we have 3 different rules for you to define continuity. We have less than 30 minutes and we are out of here, but let's ensure we stay focused, because this next thing we want to talk about is also a very, very important point. We have 3 different conditions that must be fulfilled if you're going to talk about the continuity of a function. So a function is said to be continuous if these three things are fulfilled. If these three things are fulfilled, you talk about a function being continuous. Number one is that your f of x naught, whatever x naught was, must be defined. Now, if any of these three things is not fulfilled, you can obviously state that your function is not continuous. All right. Now, the second one is that the limit of f of x when x was tending to x naught must exist. And then the third rule is that when you go on to find the limit of your function f of x, of course, when x was tending to x naught, it must be the same thing as f of x naught. These three conditions are key for you to say a function is continuous. So these are the three conditions for continuity in calculus. Now, you will see some situations where once you just see that one of these things is not fulfilled, you can obviously say it's not continuous at this point. So without wasting time, let's try and get into something quickly. So I'm going to post some questions to you, and you're going to tell me if this is continuous or not, and you're going to identify at what point you feel it wasn't continuous. All right. Now, we have this question. We have f of x being equals to x squared plus 1. Now, let me solve this, and then you'll probably solve the rest that comes with it. When you have questions like this, when you're asking for continuity, you said, we said f of x naught. The meaning of x naught here means values. You see, x naught could be any value. X naught could be any value. X naught could be 2, could be 3, could be 4, could be -5, could be minus half. We said it's defined. And then we also said the limit as x was tending towards x naught exists. Now, look at something. If you fill in values of, is there any value for x that you feel this value, this function will not be defined? Because once you can get one situation where this function will not be defined, then you can obviously state that this thing is not continuous at all points. So what do you want to do? If you identify the domain of this function, you will recognize that this thing has a broad domain, because I do not see the domain. Obviously, the domain will be, I've explained domain already, so I don't need to say much of that. Domain will be -infinity to infinity. You say why? Because if you fill in any value for x, negative, whatever it is, you fill in any value for the positive side of things, you would never get a situation where this thing will be undefined. It's going to be defined at all real values, at every real values. All right. Now, let's just pick a quick, just a trial. Let's take for instance that your x naught now, let's say our x naught is 2. Just as you can put in anything right wherever you are. You can fix any value and try if it will work also. So look at it now. We put in x naught as 2. So does f of x naught, that will be f of x, or x or f of 2 rather, that will be 2 squared plus 1. That will be 4 plus 1. That will be 5. You can see it's defined. It's not undefined. You know situations where you used to get something not being defined, when you're having square root of maybe a minus number, or you're having something over 0. Points like this is one of the things you want to avoid. Now you have this. Let's now examine. We already saw that f of x naught is defined. This is it. It's defined. Now we need to go on to find those limits as x was tending to x naught. Does it exist? So let's say the limit of f of x when x was tending to 2, because x naught is 2 now. Does it exist? That means we are saying the limit of x as it was tending to 2 for x squared plus 1. Does it exist? Of course, you know what to do. We have done this a couple of times now in this class. So all you need to do is go on and fix this. Fix this here, you get 5. I don't need to do that again. You know what to do. You put in your x as 2. Does it exist? Yes, it does exist. So you can see obviously that this limit exists, right? So the first condition, which was that f of x naught is defined. We can see that f of x naught was defined. Now, in case x naught was 2, it's defined, perfectly defined here. We went on to check if f of x when x was tending towards x naught was existing. We saw it exists. So the last but not the least thing we have to do is go on to check if this, what we have here, is equals to this. And what does it is? Are they not equal? Of course they are equal. So the okay, quite bad. Please, can you indicate if you can still hear me? So, okay, can you still hear me, please? Am I still audible to everybody? Okay, so you can see the condition that we set, the first, second, and third, has been fulfilled. Don't get this confusing at all. We just, of course, we had this function. We wanted to check if there was any point where this function will not be continuous. We just picked a random number. Of course, I've set the domain to be minus infinity to infinity. This means I was very positive that you don't have to, anything within this band, it will still be defined, because I'm so sure that there is no value in this place that will make this undefined. So the first was good. Now, I went on to just put a dummy x naught, and that was 2. And I got that my f of x naught, which was f of 2 in that case, was 5. Of course, I can see that that was defined. This is it being defined. Now, I went on to find the limit of f of x when x was tending to 2. I got my answer to be 5. I saw that it exists. Then I went on to check if the limit of this, of f of x when x was tending to x naught, was the same thing as the function of the x naught. And I saw that they're the same thing. So obviously, I can obviously proceed to define, to say that this my function is continuous. Now, this looks nice and simple, but let's talk about some other ones, and you will see some situations where this may not be the case. So let's solve another question, and let me see. In this case, I would love you to throw me your answers. Let's do this more orally so that you can get the best from what we're saying. So look at this function now. We have this function now. You tell me if this function is continuous. We have 2x over 1 plus x squared. Can you state if this function is continuous, or could you identify any point of discontinuity? That means, for instance, is there a place where you know that this function will not be continuous, right? So if you look at this function also, go on to, I just rush through this, go on to fill in any real values there. Your function will always be continuous at all points, because there's no value for x that would make this discontinuous. If you can identify any, please, you can write it in the chat box. If there's anyone you know that, okay, I know that at x equals maybe 3, it will not be continuous. There's nothing like that. So obviously, this is a continuous function. Now, let me write another one. Look at this. Imagine you had your f of x being equals to x cubed minus 2x. All right. Is this function continuous or not? Could you identify any point where this function is not going to be continuous? Do you know any point where this function will not be continuous? So you have to start from this first rule. Is there an x naught? That means a value for x. That's the meaning of x, a value for x, in which this function will not be defined. Is there anything you know that x can be that will make this your function not defined? You can go on to start finding. Then after you do that, obviously you try these other two rules. Of course, if this is not, if there's a place where the function is undefined, you don't need to even try the rest, because once there's a place where it's undefined, then that function is not continuous at that point. Of course, I'm not sure anybody can produce any answer here, because I can tell you for certain this function is continuous, all right, for all real values. That means values between minus infinity to infinity. For all values within this band, these two functions are continuous. Now, let me now write one, and I will see if you're going to get this. Look at f of x being equals to 1 over x minus 2. Now tell me, is this function continuous, or can you identify any point of discontinuity, any point that you know that this is not going to be continuous? Look at this function. We have dealt with this and this. Can you deal with this? Is this function going to be continuous, all true, or can you identify any point of discontinuity? Okay, somebody said 2. Now that person looks very much correct, because you see, if you fix in the value of 2 into this point, you'll be having 1 over 2 minus 2. That'll be 1 over 0. Can you see that at the point x being 2, your function will, this f of, that means in the meaning of this is that, look at the very first rule. That means f of 2, that means when x was 2, is undefined. Look at it here. You can see. That means, we said f of x naught. That means any value of x, it must all be defined. And we are able to identify already that x being 2 makes this function undefined. So we can see that we have a discontinuity at the point x being 2. All right. Now look at something. Let's look at another one. Look at this one. And let me see what your answer to this will be. Let's say I have this function. I have x squared minus 4 over x minus 2. Is this function continuous, or can you identify any point of discontinuity? I'm sure, and I believe everybody should be able to flow with this class. We're looking for points where this function will not be defined. Is there any value of x that will make this function undefined? Now, everybody is saying the same thing they said the previous time, because obviously the denominator is the same thing as the previous question we solved. Now, the previous question we solved was, let me write that side by side here. We solved for, I believe, is it not 1 over x minus 2? Yes, this was what we solved for. So, of course, everybody also went on to say, at the point x being 2, this other function will be discontinuous. Now, but there's something I need to introduce to you, that yes, you are very correct, that this point, because at f2, the function is undefined at this point. It's undefined at this point. So you are very correct about that. But the next thing you need to understand about discontinuity is that it is very possible for you to remove discontinuity. So if you see a function that it's possible for you to remove discontinuity, we call that function removable discontinuity. Now, look at this first function we had. We identified that x being 2 makes this function discontinuous. But the question is, could we remove that point, that discontinuity? No. In this particular one we saw before, we could not remove it. It's not all functions that are discontinuous at the point that we can remove the discontinuity. There are some functions that we cannot remove it. There are some functions we can remove it. Let's check if we can remove this discontinuity. How do you remove discontinuity? How do you remove discontinuity? What you have to do is to try and simplify this function and see, is there a way you can rearrange this, simplify this in such a way that that point of discontinuity will be removed. So you have to extend your function to another function. And of course, look at how we're going to do that. X squared minus 4 is the same thing as x squared minus 2 squared. don't forget I've been talking about difference of two squares, very, very important aspect of algebra. So of course, x squared minus 2 squares is the same thing as x plus 4, or x plus 2, and x minus 2 over x minus 2. Look at what I just did. I have not done anything wrong. I just rewrote my function as this. And by rewriting my function as this, I'm able to do something. I'm able to remove the discontinuity, because what was causing the discontinuity was x minus 2. By rewriting it this way, I'm able to cancel this out. And now I have extended my function. In this case now, this function f of x now, I've extended it to a new function g of x, of which this g of x is now be x plus 2. And I want you to understand that the graph of these two, this g of x and this f of x, they are going to be very similar, identical. All right. So look at now. This was the initial function they gave me. I identified it had the point of discontinuity at x equals to 2. So I extended my function by removing the point of discontinuity from it, and I was able to get this function. In this case now, you can go on to now check again. Will this function, will it be discontinuous at that point where you said it was discontinuous in the previous function? You said this function was discontinuous at x equals to 2. Now, go and put g of 2 now. Let's see. What does g of 2 give you? 2 plus 2, which is 4. It's not discontinuous again. So you can see this is what we call removing discontinuity. So when you have a function and you identify a point of discontinuity, like look at this previous one now, we could not remove the discontinuity. So we just say this function is not continuous. It's not continuous at the point x being equals to 2. But we saw another function, and we also identified that this function was discontinuous at x equals to 2. But the question was, could we remove that discontinuity? So we went on to try to simplify our function, and we discovered that we could remove it, and we extended our function. That means we produced a new function, g of x, which is an extension of the former function, which was x plus 2. Then we went on to cross-check again. Do we still have the point of discontinuity? And we discovered it doesn't exist again. That means we have successfully been able to remove the point of discontinuity. Let me get you to try this question out and tell me what's going to happen here. You will tell me if you are able, if first of all identify if it has a discontinuity, then you also identify if it's removable. That's the two things I want you to do. So look at the function right here. Tell me if this function is continuous. If it's not continuous, tell me at what point it's not continuous, and also identify if it's a removable discontinuity, if this function has that, if you're able to remove the discontinuity from it. All right, look at this function. This is the function right here. This is the function. So first of all, go on to ask yourself, is this function continuous? Is this function continuous? Then if you discover it's continuous, then you tell me it's continuous. Then if you discover there's a point where it's not continuous, then you tell me, okay, at this point, it's not continuous. And then I will ask you, could you remove the discontinuity? Then you will give me my response. So first of all, is this function continuous? Okay, so somebody is responding, he said it's continuous at -2. Okay, that looks very believable. Because, of course, don't forget, what makes me to define a function as being continuous is that these three things are being met. The very first one is that your f of value for any value for x, any real value of x, must be defined. I could just check up this, and I saw that if I go on to fill in x as -2, because I can see the denominator has x plus 2. If I put in x as -2, my function will be having this over 0, which is not defined at that point. So I already know that continuous at -2. All right. Now that I know that it's discontinuous at x equals to -2, what do I want to? The next question is, could you remove this point of discontinuity? Okay, what you have to now try and do is to try and simplify your function. That's how you're going to know if you could remove it or not. So if I have this function, I want to try and remove it. Of course, let me try and take the limit of, okay, what's the breakdown of this function? This function can be broken down to, of course, this is, I think, x minus 5 and x plus 2 over x plus 2. What I just did here is to factorize this numerator. This is what you're going to get. I believe everybody understands how to do that. So if I do this, of course, I can take out x plus 2. Now, I have extended my function to get a new function, which is g of x here, which was x minus 5. Now, you want to confirm, has this point of discontinuity been removed or not? So go on to put x being equals to minus 2, which was the point where you had discontinuity before. So if you put x equals to minus 2 now, you'll be getting minus 2 minus 5, which will be equals to what? Minus 7. So you can see that that discontinuity doesn't exist anymore, but it did exist in your function initially, but you have successfully, by just simplifying the function, removed the point of discontinuity. And now we are having an extended function, which I told you already, the graph of this function and the original function, they are very identical. So let's see, look at f of x here, being equals to 2 over x. So guys, is this function discontinuous? And can you remove the point of discontinuity? Is this function discontinuous, and can the point of discontinuity be removed? Let me give you 3 on a row so that we can perfect this knowledge. We have another one, x over x squared minus 1. And the last one here, we have fx equals to x squared plus 2 plus x minus 2 over x minus 2 squared, or x minus 1 squared. So guys, tell me now, the very first one, the very first one, is it discontinuous at any point? The very first question, that's this first one. Let's call this 1, 2, 3. Is it discontinuous at any point? Of course, yes. The first one, if you go on to fixing x as 0, you know that it's discontinuous at that point 0. So the next question is, can you remove this discontinuity? No, I do not see a way you are going to be able to remove the point of discontinuity in question number 1. All right. Now, for number 2, is it discontinuous at any point, or is it a continuous function? Question number 2, the function you have there, is it continuous? When you look at question number 2, you can see already that this function is continuous at almost every point, but there is one place you're going to have issues with this function. If you fill in x as 1, that'll be 1 squared, that'll be 1. 1 minus 1, 0. So you can see obviously that x being equals to 1, or if it was even equals to minus 1, because minus 1 squared is still going to be 1, and 1 minus 1 is going to be 0. So you can see that at the point x being 1 or minus 1, this function is discontinuous. So obviously, you do not want to, you cannot say this function is continuous at all points. Now, the next question is, can you remove the discontinuity? Can you check it? Can you remove the discontinuity? Well, I do not see how. There's no way you want to simplify this, because if you decide to make this x squared minus 1, if you decide to go on and try to simplify, I'm not seeing how you are going to be able to remove the point of discontinuity. That means you want to have maybe x over x plus 1, x minus 1, probably using difference of 2 squared. I'm not seeing how we're going to be able to cancel the situation around discontinuity there. So this is the point where it's discontinuous. Now look at this last one. Is it continuous, or is there a point of discontinuity? Is it continuous at all points? Okay, now somebody says discontinuous at 1. Good. Check this out. If you fill in x as 1 in this third function, this is 1 minus 1, that is 0. 0 squared is still going to be 0. So obviously, at point x being 1, this third function will be discontinuous. Guys, I hope you are getting the best from all this. These are questions. I believe this question came out in your last test and possibly could come out in your exam. If you have x being 1 here, it's going to be discontinuous at that point. Now, the next question is, can you remove this point of discontinuity? So what do you have to do? You try to simplify your work. If you want to simplify this work right here, what you have here, of course, this numerator can be simplified to be x plus 2 and x minus 1. Look at it, oh. It's looking like, oh, I can remove this point of discontinuity because I can see x plus 2, I can see x. This numerator is the same thing as this. So over x minus 1 square. Whoa, nice one. Of course, you feel very nice about this because you can see x minus 1 here. You want to cut this away. So this will be equals to x plus 2 and x minus 1. Of course, you feel you have done a good job and possibly you can remove the point of discontinuity. But one of the things you can see is that at the end of all the simplification you did, you are still having x minus 1. So that point where it was discontinuous, that was 1. If you put x as 1 here, put x as 1, you will still be getting the very same thing. It's still going to be discontinuous at x being 1. So that tells you already that it's not removable. So you cannot remove the point of discontinuity here. All right. So this is where we're going to stop for today. So we have been able to accomplish, I believe, really great things this weekend. I really believe that for anyone that followed us all through the classes, you have learned so much. We have done so much. And the next time we'll be meeting, we'll be coming into the aspect of first principles and every other thing around differentiation. So please, guys, ensure you are ready for a great test. A great test is coming. And I think I passed the information already. So please ensure you are prepared adequately for your test. And make sure you practice this. Ensure you cram your identities. Know your identities offhand. That's going to be key. And ensure you also go and recollect back your identities around trigonometry. It's really, really key. If you understand your identity around trigonometry, you're going to do really great in calculus. So make sure you do whatever it takes to ensure that you are very sound in calculus. I want to ensure that you are going to ace every aspect of your coming exam, every aspect, 01, 02, 03, 04. That's why we're here. That's why we're burning the midnight oil. I understand it's stressful. I understand many of you are stressed out. I understand you are putting in your best. I understand it's a sacrifice, but it's a sacrifice that will pay out eventually. So keep at it. Don't give up and don't get tired. Just keep pushing. This is the sacrifice you have to give for success. And I wish you guys all the best. Thank you and good night.